Let me show you how to be a good Bayesian.
My guest today is Luigi Acerbi, Associate Professor of Artificial Human Intelligence at the University of Helsinki, where he leads the Machine and Human Intelligence Lab. I've been following Luigi's work for years, and it sits right next to a bunch of episodes we've done recently. Luigi is, above all, a tool builder. He came to Bayesian inference from theoretical physics and computational neuroscience, chasing one idea, that inference and prediction might be the thing that brains, science, and machines all have in common. Out of that came methods like VBMC and BADS, and the PyVBMC and PyBADS packages that a lot of scientists actually use. More recently, Luigi has fallen in love with neural processes, and we get into why transformers turn out to be such a natural fit for them. We talk about his amortized conditioning engine, active data acquisition, changing priors at runtime, and where all of this is heading, foundation models for inference. We even get into small local LLMs and Bayesian decision theory for agents. This is Learning Bayesian Statistics, episode 161, recorded May 27, 2026.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. What's a Bayesian? It's someone who cares about evidence.
Welcome to Learning Bayesian Statistics, a podcast about Bayesian inference, the methods, the projects, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. For any info about the show, learnbayesstats.com is la place to be. Show notes, becoming a corporate sponsor, unlocking Bayesian merch, supporting the show on Patreon, everything is in there. That's learnbayesstats.com. If you're interested in one-on-one mentorship, online courses, or statistical consulting, feel free to reach out and book a call at topmate.io/Alex_Andorra. See you around, folks, and best Bayesian wishes to you all.
Luigi Acerbi, benvenuto a Learning Bayesian Statistics.
Grazie.
Yeah, I would love to do the episode in Italian. My Italian is very, very rusty. I used to speak pretty good Italian, but then I went to Argentina and had to learn Spanish, and the two languages are so close that
Yeah, true.
like it just like my brain just confuses it. So I guess I need to go live in Italy again.
True. Yes. I mean, actually, I noticed that my wife is Spanish, so let's say, so we kind of, we speak English. The official language is English in the house, but we kind of, so we pick up each other's language. So let's say, so I speak a bit of Spanish, and she speaks, actually, she speaks way better Italian than me, than my Spanish. But anyways.
Yeah, okay. Yeah, I mean, that's now the weird thing is that, so now when I come to Italy, my Italian comes back after a week, more or less, but the first week I'm the classic proverbial French that people hate, who think they speak Italian, but they actually speak Spanish. And I know Italians hate that, and I don't do it on purpose, so
Okay.
I'm
Okay,
sorry.
I don't mind. I don't mind. It's close enough.
Awesome. Well, really, really happy to have you on the show, because I've been following your work for a few years now, and you do super interesting stuff related to a few episodes we've done now on the show, especially with Marvin Schmidt, and even more recently with Stefan Khalef, episodes 107, 157, 158. These are going to be in the related episodes for this one. But so for today, let's start as usual with your origin story, Luigi. What are you doing nowadays, and how did you end up there?
All right. Yeah. Well, thanks for having me. Really, really happy to be here talking to you. And okay, so where I'm now. So where I'm now physically, I'm in Helsinki, and so I'm a professor, associate professor of artificial human intelligence. The work we've been doing recently in the past few years focuses on using modern machine learning tools to do Bayesian inference. That's That's kind of the broader area. And we apply these tools to various domains. One goal is to do just predictions and inference, but let's say one application is obviously model fitting, in the sense that you have a model, you want to infer the parameters of that model, you want to make predictions with that model, and nowadays, let's say, there are powerful neural networks that allow you to kind of do that fast, and anyways, that's the direction that we are following recently. But how I got here is a much longer path, and so I'll try to compress it, like literally how modern agents, when you do compaction. So I'll try to compact a very long string of tokens into a few sentences. Originally, say, as we were discussing like a little ago, so I mean, I grew up and studied in Italy, but physics, that's kind of where I come from, theoretical physics. But then for my PhD, I moved to the UK, Edinburgh, and where I studied was researching computational neuroscience. At the time, it was called computational neuroscience and neuroinformatics. And the brain is very confusing, especially if you don't know much biology, and I didn't definitely know enough biology at the time. No, now. And neuroscience is even more confusing because also, I mean, it's very interesting, but it's also very, very confusing. And as a physicist, always, one of the things that teach you is that you want to simplify things as much as possible. So let's say, and trying to simplify the brain is hard, possibly. Let's say, there are also, let's say, disciplines or currents that say that you shouldn't try to simplify too much. But anyways, that's kind of the temptation. You want to kind of come to the simplest possible description in a way. And I was kind of flailing to try and to make sense of it. And then I read a few influential things, and I studied a few influential things. One first, I think it's one book that kind of influenced me at the time and actually convinced me to go to computational neuroscience was On Intelligence, and the idea that what the brain is doing is prediction. And that seemed like a beautiful. So everything that the brain is doing, everything like in the cortical columns in the brain are doing is just kind of predicting inputs. And I found that a very powerful idea at the time. And then I started researching in computational neuroscience. And then I was exposed at the time to Bayes. And that was in a course. As a physicist, I had absolutely no idea of what Bayes was, because that's not taught. It wasn't taught at the time. So let's say I just had some kind of sprinkling of classical statistics. And then when I was kind of exposed to Bayes' theorem, it's like, okay, this explains everything. And then essentially not just Bayes. That just was Bayes kind of in a machine learning course, probabilistic machine learning. But and then let's say the idea that the brain does Bayesian inference, and what the brain, essentially what it does in a nutshell, everything that the brain does, not everything, but let's say a big chunk of what the brain does is being a sort of statistical inference engine. That's kind of, trying to make sense of the external world by building model, assigning probabilities, computing posteriors. And I find that idea very alluring. And then essentially, that's kind of everything kind of came together. So essentially, starting to study this version of kind of neuroscience, cognitive science. Then, of course, then I became more practical with the tools of Bayesian inference. But then again, I was kind of studying Bayesian inference because the system I was studying was using Bayesian inference. So I was kind of trying to study a system, But then, you can use the tools of Bayesian inference to study the system which uses Bayesian inference. So I was doing kind of sort of a Bayes inception, in which I was using Bayesian tools or Bayesian models to understand a Bayesian system. And people have called this doubly Bayesian. I argue that what I was doing then became triply Bayesian, because then I started using tools which themselves used Bayesian inference to perform their task, and I will get to those later. So anyway, so I had Bayes everywhere in my life, and then essentially, so I started building tools to do model fitting, and then I kind of like that part. These models are complicated. Requires complicated tools to fit the parameters, and then essentially I started developing those tools as part of my job, because anyways the hammer is the same. You have Bayes, and whether how you apply it is up to you. So everything became essentially building tools, and then eventually I kind of moved even more into machine learning, because again, as I tend to say, I'm interested effectively, again, in this idea that inference is kind of some sort of a foundational, fundamental concept in the universe, or that's useful, say in biology, is useful in science, and so I'm studying it, in all these different areas, and then so essentially, so it was kind of natural to move to machine learning to do, the things we are doing now, because again, studying, say the end system in a way is relatively relevant. What kind of the core element that stays the same is exactly this idea of inference and prediction.
Yeah. Makes sense, and it's really interesting to have to hear you about the whole arc of your career. So you've touched on it a bit, but maybe even more specifically, is there anything in particular or someone in particular that drew you to Bayesian statistics specifically, and then to amortized inference and neural processes?
So the path. So yes. So let's say I had a few professors at when I was still, let's say, a master student and a PhD student in Edinburgh. At the time, there was, say still there is a very, very vivid and interactive machine learning and computer science, and also at the time, say, neuroscience, computational neuroscience community. And so there was a lot of interconnection between our cohort of computational neuroscientists and the machine learning cohort. In fact, let's say people were kind of swapping all the time. I think I said there was one course which I took at the time, which was something called something like probabilistic cognitive modeling, which is similar to the course I'm currently giving. And so yeah, that introduced, essentially, among other things, the idea of the Bayesian brain, or the idea that the brain does probabilistic inference. At the time, it was taught by Peggy Series. She was a lecturer at the University of Edinburgh at the time. And so that was quite inspiring. And then kind of I took that route, and then I kind of never really left it. And coming to today, you were asking about, well, what I'm doing today. You were asking about the neural processes. So actually, this is kind of funny, because neural processes are essentially neural networks that learn to do inferential and prediction tasks. And I stayed away on purpose from a neural network for most of my life. That was a conscious choice, possibly wrong, actually, surely wrong. And the reason is that, to say, when I was a PhD student at the time, say neural network, deep nets. Well, actually, at the beginning they didn't even exist. Deep nets exploded, let's say, in 2000. Famously people mention AlexNet in 2012. And so as the year in which deep learning started working, and I started my PhD in 2010. So let's say, so when I started, it wasn't quite working yet, and but still, let's say, at the time, for a number of reasons, let's say, I wasn't interested in neural networks, and that was a mistake, obviously, in hindsight. But so let's say, so I kind of took me a while to kind of get back to neural network. Let's say I did it very late in my career, like I did it like probably a few years ago. And what kind of convinced me to come back were neural processes. So neural processes, so there were these beautiful papers in 2018. I kind of discovered them maybe a couple years later, 1-2 years later. And this, so the first author, Marta Garnelo, I think at the time she was at DeepMind, I think. Now I'm not sure, but let's say, and this was anyway, so a group at DeepMind, if I'm not mistaken. And the idea of the original neural processes paper, there are kind of two papers. One is called neural processes, the other conditional neural processes, but they're similar in scope. The idea is that you can train a neural network. At the time, it was kind of like a standard multi-layer perceptron, so like, a relatively simple network. So normally how we would train a network is that you have a data set, and you train on a single data set. I mean, that's how people used to do it. So you would train on a single data set. Maybe you have a held out data set that you use for validation. But you train on a data set, and then you have to perform a task, and you have a single data set that you train on. The idea that they had at the time is that instead of training on a single data set, you train on a data set of data sets. So let's say you have a lot of kind of small data sets that you're training on, and for each one of them, you're training your network given this small data set to do a task like, predicting, for example, giving us a small data set of points, like, on a regression problem, I give you X and Y value for each. So that's my data set. Then, I want to predict, the value of the function at other points, other values of X. So what you do, you take your data set, you split it in a training set and a test set. And in the neural process literature, you would call them context and targets. And by the way, context will come back. And the idea is that, okay, so now I'm training my neural network to, given the context, to predict the targets. You do it once, twice, 1,000 times, because you have a lot of small data sets that you can chop. You chop in context and target, and you repeat this procedure a lot. So now what you're doing is you're training your network that to do this task, this predictive task, and then at runtime, now you give it another data set, which you call context, and you give it a bunch of targets to predict, and your network has learned to solve this prediction task. Okay, so, but the point is, of course, it's done by learning, by seeing a lot of different data sets. And of course, I say the idea is that you would use, for example, some generative process or a data set of data sets to train your network in such a way that it kind of learned the statistics of the task, such that when you present a new instance, it can just resolve it immediately. And nowadays, well, already at the time, but nowadays, we would call this a form of amortized inference, in the sense that you can do this training on many data sets, and then you just deploy it, and then at runtime you can do your predictions on new data points, kind of instantly. And I found it was beautiful because it's for example, when you condition on a bunch of points, that's a set, typically. So unless it's time series, but let's say, typically it's a set. That's also a property. So kind of you want to satisfy some properties of probability of stochastic processes. Like, for example, if you change the order of the points, your prediction shouldn't change because it's a set. The data points are exchangeable. If you say that's the term. And they use a structure which is called a deep set to represent this set with a neural network. And so essentially, it's a mix of Bayesian statistics, stochastic processes like Gaussian processes, for example. But let's say, and uses deep networks. But let's say it's it's also mathematically beautiful because let's say you have these properties that gets which are preserved. The fact that you can permute your nice small set of data. So anyways, and then so you have something that learns a task. And I found that actually really, really interesting and promising and kind of very elegant in a way, as opposed to maybe kind of just, okay, I train a network to do a bunch of stuff. Like there is some elegance to the concept of a neural process, and I fell in love with that. And then I started digging, and and then we get to today.
Super cool. Yeah. Damn. Thanks for all these details. And actually, so one of the things you've been working a lot is a concept we haven't touched on yet really on the show, which is called VBMC, for Variational Bayesian Monte Carlo. And so you describe it as like Bayesian optimization, but for finding the full posterior instead of just the optimum. What does that mean? What is the core trick, let's say, and the core method that makes that possible?
Okay. Cool. Okay. So yes. So to connect a bit to what I just said. So before I kind of mentioned in passing Gaussian processes. So let's say, so that was kind of my intermediate phase, which is still ongoing. Let's say so before I moved to kind of I came back to neural networks. So actually, not I came back. I came to neural networks. So I was kind of still in the camp of kind of traditional Bayesian non-parametrics, which uses kind of and the workhorse of that field is Gaussian processes. And so I will assume that your audience might have heard of Bayesian optimization, which is the idea is that you have essentially you want to optimize a function. This function might be expensive. So let's say you have a limited number of evaluations you can take to find the optimum of this function. So what you would do, say kind of traditionally, is that one approach is called Bayesian optimization, and the idea is that you take your evaluations, you can use some form of regression or surrogate model that you're fitting to these points, and then you use this surrogate to decide, okay, where to sample next. And the goal of this procedure is that, of course, you want to find points which are promising in the sense that they tell you where the optimum might be, and they kind of guide your sampling procedure so that you can find a good candidate for the optimum. And as I said, the workhorse for this is a Gaussian process, which is a Bayesian kind of mathematical object, which has a lot of nice, very, very nice and pretty properties. Everybody kind of loves Gaussian processes when they can use them because they're really, really mathematically beautiful. They have a bunch of kind of downsides, but otherwise, I say, they're really practical, and they have, again, so for example, some of the properties that they have is that they behave very well with little data. So let's say, because essentially, they're a Bayesian kind of construct, so they come up with a strong prior for what a function looks like. For example, function, depending on some choices you made, but typically you assume the functions are somewhat smooth. So let's say, so your function is not going to do something crazy, but it's kind of, it interpolates between points nicely. And so people use it a lot in optimization, and that's kind of Bayesian optimization is kind of it's a field in itself. It's a big field, and there is a beautiful book by Roman Garnett recently came out, Bayesian optimization, and I really recommend it. It's a really, really awesome book. And anyways, so that's optimization. But I'm Bayesian. I don't want to just optimize. I want to find the full posterior. And so let's say, so the idea I had many years ago was, well, because when you're building your surrogate model using a Gaussian process, you're kind of representing a function, and of course at the end you only care about the optimum. But I say, no, you're kind of representing the shape. So can we use that? But where the function is not an arbitrary function, but it's effectively a posterior, and more specifically a log posterior, so the logarithm of the posterior, and it's a function. So can I use something similar to Bayesian optimization to kind of sample this distribution? When I say sample, I mean evaluate at arbitrary point, not sample like as in MCMC. So so I'm just evaluating this function at a few points, and then I use this very powerful interpolator to kind of build the entire shape. And then instead of optimizing it, what I want to do with this shape is, I keep all the shape, and that's the posterior. So I want to learn the shape of the posterior by a few carefully selected points. And the reason to do that, well, of course, let's say if your function, like if you're working with a model that you can write in Stan or PyMC, probably that's not very expensive, so you can run MCMC. But there are lots of models in many disciplines where you can write your model, your log likelihood, but evaluating it is expensive. So let's say, so you can calculate it, but let's say it's expensive. So let's say, so and that's essentially the idea of VBMC. That's essentially does the same job as Bayesian optimization. So it lets you get the shape of the function, but instead of being expensive and taking maybe MCMC might take tens of thousands, hundreds of thousands, even million evaluation of your function, which is your function even takes 1 second per evaluation. You need to wait 1 million seconds to do a full MCMC. While VBMC typically, with a few hundred evaluations, you can kind of get a good reconstruction of the shape of the posterior. It's not perfect, we can discuss it, but let's say, so it's again, it's a very good approximation typically in low dimension. That's the caveat. Essentially the big caveat is that this works well in low dimension because you're building this surrogate, and as anybody you work with GPs, Gaussian processes, they work well in lowish dimension. Let's say, if you go above, 10, 20, 30, let's say, it kind of gets hard because just, you don't have enough point to kind of interpolate the shape of the function. So it works for models that have up to 5, 10, 15 parameters.
Damn. Okay. Yeah. So that means in which cases would you use that concretely? I think it's going to be interesting for listeners to understand. And while preparing for the show, I was actually looking at your PyVBMC package, which looks super cool. I encourage people to go in there and give it a try. So actually, can you tell us when should we reach for that package? When is it not appropriate? I think it will give us an idea of when these kind of methods are most powerful.
Yeah, I think that's a good point. So one thing I want to say that, so the reason why I moved to kind of doing these things is exactly because I came from the practitioner side. So I was building models and fitting models, and it was slow. So let's say, so I say, okay, I had an actual problem I wanted to solve. And many of the users of VBMC or of the other, our other tools like BUDS are practitioners. They work in cognitive science, computational neuroscience, and now, it's kind of spreading to other fields, but let's say, so if you look, for example, at the website, there is always, I have big FAQs that are going to tell you, when it works, when it doesn't, because exactly we kind of want to be clear for the user and say, and you need to be very honest about what a method does and doesn't. So in the case of PyVBMC, so when should you reach it out? First of all, let's say, so if you can code up your model in Stan, in PyMC, everything is working fine, you're good. So there is no need for PyVBMC. So the point is, when say, if you know that, so if you have a problem, you have a problem, in the sense that, okay, so for example, you have a model which, for a number of reasons, doesn't, sometimes you can't even code it in say, in PyMC or in Stan, because say there are some aspects which are non-differentiable. So let's say, so you're in trouble because you say these methods would need to compute the gradients, automatically to do MCMC. So for example, if you're for a number of reasons your function is not an easy function, but say there is some sort of a complex process that you need to solve, and this emerge in the computational sciences. So for example, if you're building a statistical model from scratch, this is rare because, say, by definition, you think in terms of easy, nice distribution that you can fit. But let's say, if you come from the science, it's kind of the opposite in the sense that, you don't think in terms of statistical distribution, like, you think in terms of the process that you're trying to model, and that might not kind of behave like any of our nice distribution that you can get out of a package. Let's say, so essentially, so I would say most of the usages come from science and engineering, where you're kind of trying to model something which is kind of has its own process that you're trying to model. And then, and the kind of symptom that you have, it's not that the process is complex or not, but the symptom that you have in practice is that, for example, it takes time to compute. So let's say, so just, evaluating one point, one parameter, the log likelihood or log density at one point, takes the order maybe 1 second or something. 1 second might not seem a lot, but let's say it is a lot, because again, if you need to sample, like if you evaluate your function in, again, tens of thousands of points, that's, you start feeling it. So I'd say speed typically is kind of the first symptom that people get aware of, and this might happen, let's say, even if you have a classical kind of easy model that you could fit with with Stan, etc. But maybe for some reason, let's say either you have a lot of data, or there is something, let's say, that makes this particularly nasty. And then let's say, so again, maybe the time factor. So I would say the time factor is the kind of the first one that people would notice. So if you're in that case, then there are a few kind of other check marks that you need to check, because, for example, since we use this Gaussian process as a surrogate, and so essentially you're doing interpolation essentially you're doing interpolation in these spaces. So we kind of know, let's say, from using Gaussian processing regression in Bayesian optimization. So these things work well, they up to order of 10 parameters, or which means maybe you can push them a bit further. You can maybe get to 15, etc. But say, so if you, for example, if your model has 50 parameters, I would not recommend PyVBMC in its current form, at least. Who knows? Maybe we'll push it to high dimensional. But again, it's like other problems in Bayesian optimization. So why, for example, there is that limit? Because in Bayesian optimization, in the end, using the surrogate just to kind of to guide you to find a good point, but then you're evaluating your function. So optimization is an easy problem, because it's self-verified in the sense that you can evaluate a point, you measure it, and you can just check whether it is a better point than the previous one. Then you know whether you're improving your optimization. It's kind of it's self verified. That's not true for Bayesian say Bayesian inference, because say you have a distribution, and it's absolutely non-trivial to diagnose whether your distribution is improving. What does it even mean? Let's say, so you just get a different distribution. But let's say there is no immediate ground truth that tells you whether something is correct or not. So anyways, so it's a way harder problem. So let's say, so there's a lot of things that PyVBMC does to make sure that inference is going correctly. So let's say there's a bunch of diagnostics. But anyways, so let's say, so this check the speed of your evaluations. and check the dimensions. These are kind of the starting point. Then, there are other things that you can start looking. But I say, so if you are in this case, then, then it might be useful.
Yeah, okay. Very practical, thanks. And that's indeed what I really love from your research is that it's not ivory tower research. It's really, okay, I have this problem. How do I solve that? Not only for me, but for everybody. So I think that's what makes what you're doing and also what the whole group at Helsinki University and Aalto is making. It's just always very, very practical and helpful. And so accompanying these papers with open source packages as you do is always a great way to make sure papers actually go through to practitioners' workflows, which is in the end what I'm guessing is the most useful. And so you have another package actually that's called PyBads, BADS. Can you tell us what the difference is? Like, what is BADS in comparison to VBMC? And
Yes,
when is
okay.
that helpful? Which cases does it help?
Yeah, thanks. By the way, I didn't mention what VBMC stands for. That's it's a mouthful. It's a Variational Bayesian Monte Carlo. So it was. I didn't check any PR or any. It wasn't to find like a good name. But anyways, BADS is probably nicer. Is Bayesian Adaptive Direct Search, and what is it? So I kind of came earlier, and I think it's quite widespread now, and it's an optimization method. So let's say, so VBMC is, me trying to do Bayesian inference properly. So BADS came earlier. So it was kind of, okay, I'm trying to solve these model fitting problems. Let's treat them as an optimization problem. So let's say, just, maximum likely estimation. So you just want to find the parameter that maximizes, the probability of your data, the estimate data, your log likelihood, your likelihood. And so anyway, if you strip of everything, it's just an optimization problem. So you can use any optimizer you want to do maximum likely estimation. You take your favorite optimizer. If you can compute the gradient, you compute the gradients, and you go. So the problem is that most of the problem, they say, of the models that we had at the time, and still nowadays, in the sciences, for example, they're not nice. You don't have gradients, etc., etc. So I was looking. So you enter the realm of derivative-free optimization in the sense that you need to do optimization without having gradient. That's hard because then, given a point, you don't know exactly where to go because the gradient helps you, knowing where the minimum is. As it's, a promising direction is, let's say, without the gradient, you need to figure it out. And that's actually, I had a kind of rabbit hole for 1 year, kind of studying optimization, studying all sorts of different methods. But anyway, so I was very unhappy with existing methods at the time. I was still doing, computational neuroscience and model fitting. So I said, okay, I need to write a better method. And, which works, right? Because there were many methods which were published, will look very, very good. And then any method I tried broke on our problems. Like, nothing works. And it was very frustrating at the time. Then I realized how, okay, maybe I shouldn't say it, but let's analyze how, publishing machine learning works. And, okay, so one thing is what you say in the paper, one thing, then trying to use the method in practice. And, literally most of the papers I tried broke on, first impact with a real problem. So I said, okay, now I want to solve this. And I mean, solve it is a big word, but I want to produce something that is usable. Okay, let's say it that way. And so that's essentially BADS. So BADS, we talked about Bayesian optimization before. So BADS is a hybrid Bayesian optimization method. And the reason why it's hybrid is because if you use Bayesian optimization in a vanilla sense, like, just, kind of out of a textbook, it doesn't work. So that's the secret. It doesn't work. So you need to use a lot of other tricks, which, modern packages use kind of, behind the scenes. But even so, let's say many packages would break on our problems because they're kind of very nasty, and the Gaussian processes would break in various ways. Gaussian processes, unfortunately, are very nice, but also break all the time. And so what's hybrid? So hybrid, effectively, you want a method that, so when your surrogate model is good, like, your Gaussian process is good, then you trust your Gaussian process, and, and that can allow you really to kind of reach the minimum very fast. So if you have a good approximation, that can be very powerful, and you can really jump through the landscape and find the minimum. The problem is that many times your surrogate is not good. And because, your function might be very nasty, you don't have enough points to really represent what's going on. And trusting the surrogate would be a terrible idea then. Then essentially you want some sort of a fallback methodology to kind of, to still do optimization in that situation, maybe that get out of that region, which is kind of nasty, and then, go back to kind of trying to fit things with your surrogate. Now, what I said looks like a heuristic, but there is a framework which is called Mesh Adaptive Direct Search, which is, it's a paper. It's a very highly cited paper, the Journal of Optimization, if I'm not mistaken. But anyway, so it's so that gives you a framework for how to do this. So what I did essentially, I took the framework. It's a framework so you can kind of play around with different components, and I kind of built my version, which is again BADS. And the short answer is that essentially, so again, it has limits because of course methods have limits. So for example, it works up to 20-ish dimensions because of this idea that it uses these Gaussian processes. They said you can use it with higher than 20 dimension, but then that part of building a nice surrogate breaks down pretty much all the time. So you end up only with the other part, which is the kind of slower and not fast way. So you get a bad method. But if you're in a situation in which your model, your function can be modeled in some parts, not in all of it. So you can have bad parts, and and the method gets out of those. But then once in a good part, then you get this kind of acceleration because now you can build the surrogate, and then so it can be very efficient. And there's this nice thing which is kind of I think Andrew Gellman mentions it in his blog. So there's this thing that when a model is good, like and when near the optimum, near the maximum likelihood value, things are nice, because this come actually, from the Bernstein von Mises theorem, so in the sense that things eventually kind of all converge to a Gaussian, and so near the maximum like solution, maximum posterior solution, everything kind of looks like it's nice and quadratic and Gaussian. And so if you're in a good region, things are nice, and then you can model them nicely. If you're farther away, things can be nasty. But the point is, you don't particularly care because those regions are just bad. So you kind of want to exit those regions quickly and get to the good ones. So anyways, so that's why in a way BADS I think also works very well for optimization especially for models.
Okay, damn, this is also super interesting. I feel like it works in a smaller number of cases, right, than VBDM. But if you enter that use case, it's going to be extremely helpful to use PyBADS. Is that correct?
Yeah, it's actually more the other way around. Like PyBADS is more universal in the sense that a lot of people in our field. I know. I'll say. I think I say you of course say you come from Bayesian statistics, so you think everybody does Bayesian statistics, and that's what I wish. But no, that's not the reality. The reality in many scientific fields, at least in cognitive science and especially in neuroscience, people are not at the level yet of doing Bayesian inference, and they are totally okay doing maximum likelihood estimation for a number of reasons, which are also understandable because the models are very complicated. So doing Bayesian inference could be completely hellish. So I say so people are totally happy with getting half it. So they don't have any pretense of trying to find the full posterior distribution. So that was kind of my attempt with the VBMC. So that's why BADS is way more used as well, because it's essentially in the end it's just an optimization method with some tricks to make it work, etc. In harder cases, etc. So I would say a lot of people are using BADS. It is a smaller kind of community that uses VBMC.
Yeah. Okay, interesting. That's actually a good point. And I don't know if you already have a mascot for BADS, but it obviously needs to be a bunny, because that way it's BADS bunny, and I think it's a perfect marketing tool,
we should.
Luigi, so
yes, that's a good point.
Yeah, we need to get them there. That's how we'll win the battle. So that's VBDM, that's BADS, and running a running theme, a running topic in your work, especially lately, is neural processes. You said at the beginning you really love them. What was the unlock for you? What's so fascinating about them?
Yeah, so let's say it was interesting exactly because I said I was kind of wary of deep nets, because again just honestly just because in a way I didn't understand them. I mean, let's say, I mean, yes, okay, I understand them, but I didn't get them because it looks like, okay, you just have a problem, you throw a neural network at it, and then it kind of solves it, but that's a bit ugly. And then I mean, of course, say, I mean, I'm talking like a physicist, who likes to see symmetry and 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 then let's say, yeah, neural processes to me at least, they spoke to me exactly because let's say they were not completely arbitrary, but let's say there was this idea that first, first of all, the very nice idea of this kind of meta learning in the sense that you're training on a data set of data sets. So let's say, so you're kind of learning what the task is by seeing a lot of instances of the task. And so, and it's nice because each instance is kind of like a micro problem that the network needs to learn to solve. And then, it's given another micro problem and then another micro problem. And then, it kind of, and it's kind of learning to possibly generalize, across different data sets. And that's I found that, okay, that's interesting. There's something going on there, which is interesting. And then let's say I specifically liked this idea that, okay, so since, again, you are conditioning on this available data, and this is a set, you want the architecture of the network to respect this symmetry. And this is done, let's say, with the old kind of conditional neural processes or neural processes originally, with a deep set, which was proposed in a previous paper, a deep set. And which essentially it's a way to encode set-based information in a neural network. And again, it kind of, it's quite elegant. And it tells you, how, I mean, the original paper tells you how you can do it, what are the constraints that you can have, on your architecture to do this. And yeah, it's, I mean, let's say, and it's actually quite simple. Like, the basic version is quite simple. Essentially, the idea is that you have a bunch of data points. Each data points get embedded separately, and then you get a representation, and then you just sum all the representation. And since, the sum operation, is commutative, you can swap all the orders. And, let's say the end representation essentially just, it doesn't change if you change the order of your data, because let's say that just, you embed them and then you sum them. And so I found that, it was kind of very, very pleasant. Then, you can have deeper deep sets, but let's say, for example, the original neural processes and many other papers essentially kind of stop at one level in the sense that, you kind of get these data points, you embed them, and then, and then you just sum the embeddings and you get this representation. And then, you have a kind of a readout that kind of makes predictions based on that embedding.
Okay. And so that's why you're saying that transformers are a natural process architecture,
Exactly.
a natural neural process architecture. Like, I mean, because I've seen you write that, and I'm wondering what that means precisely and what that implies for how we should think about prediction in context learning, amortized Bayesian inference, and all the other topics you work on.
Yeah. That's a good point. Like, so that's why that's for me was the bigger unlock when I especially after kind of learning about neural processes, and then a few years later, again, took me a while. Everybody was talking about these transformer things, and 2017, of course, attention is all you need. But then transformer became very big, as we know. And then, yes, so let's say, so what I described before, I mean, I use that language, but so it was originally language at the time. It's like, yeah, you have data sets, you embed them, you have a representation, and then you work with that representation. Nowadays, we will call them tokens, but it's exactly the same thing. So you have each kind of data point is a token. You embed it in a representation, which is, your whatever, and, d-dimensional vector. And now you wouldn't sum them, because summing is what we were doing before in a kind of standard neural process. In modern, in the transformer architecture, you allow each token to kind of look at each other using the attention mechanism, which is just, is a more complex operation. And the beautiful thing about attention is that attention, again, is a set operation. So let's say, so there is no ordering in a transformer. Since transformers were proposed for language modeling, even originally, so actually they had to break the permutation invariance or equivariance. So they had to introduce what's positional embedding, which is something like, okay, this is the first position, this is the second position. So it's something that you need to add to a transformer to make it aware of the sequence, or it's a sequence. But otherwise, a transformer as is, the architecture is permutation, say equivariant / invariant, depending on what you do. And so you can just shuffle around your data points, and and the result doesn't change. So let's say, so it's a very, very natural kind of architecture to represent the idea of getting information from a data set, a set of data points. Each one is a token. These tokens, talk to each other by attention. You do it multiple blocks. They keep talking to each other. And then in the end, you have a representation. And now you can use that representation to do things. And if you think in Bayesian terms, what's going on here is that your network is conditioning on this data set. And now so it's kind of learning, it's kind of given this data set, then, you can take, for example, the last layer or whatever, and then, do prediction based on this layer. But say what you're doing is you're conditioning on that information to predict other stuff. And that again, it's that's why I was saying that, yes, so transformers are very natural, because in a way they supercharge, what, kind of deep sets we're already doing, but deep sets are less efficient architecture, transformers do that, this very kind of, because essentially all tokens can talk to each other, and it's a very powerful representation.
Yeah, and such a universal one also, so that makes it extremely powerful. And actually, if I understood correctly, you work on an amortized conditioning engine. It's called ACE, and another paper that you have, which is called ALINE. Let's spend a bit of time on these papers, but they're from last year, so just a bit of time, and then afterwards we'll go into what you're actually doing right now and your current work. But I think these two papers and also the blog post that you have, where you talk about, like, you make the case that you can just predict the optimum. All this work is related, and that's all from last year. So if you can go first through ACE, Amortized Conditioning Engine, to give listeners an idea of what you've been doing last year, and maybe there's something useful in there for them.
Okay. Yeah. So so essentially a couple of years ago, maybe 2-3 years ago, so we started this agenda in my group, which is we used to call, half jokingly, the amortize everything agenda. So I say we want to amortize everything. Now, I'll kind of make a correction later to this, but at the time, that's what we were aiming to do. And again, we realized that, okay, so what we just need to do is, build a big transformer that can condition on things. And essentially, the 2025 paper, this Amortized Conditioning Engine, the idea there is, okay, so neural processes, and similarly, let's say, prior fitted or prior data fitted networks, PFNs, which are also transformer neural processes. They have, let's say, architecturally, they're essentially the same. There are kind of minute differences. But let's say, essentially they enter this kind of the same world of what we call the transformer probabilistic models. So the idea is that, so you have a transformer, you can condition on data points, and all the methods until ours, let's say, so what they were doing is that they were conditioning on data points, and then, you have some target points that you want to predict at, and then, they would give you a prediction as, a distribution expressed in some way, a Gaussian or something more complex. But anyway, so you would predict, let's say, the value of the function at these data points. But we wanted to generalize that, because I don't always only want to predict values of things, let's say, or functions. So let's say, because so there was, at the same time, there was this other kind of nearby field of amortized inference, where you want to predict, you have data points and you want to predict the model parameters that generated those data points. That's, kind of classical amortized inference. So you train your model to given some data points to predict the parameters that generated those, and the kind of the field, is a subfield of simulation-based inference, in the sense that you use this data that you generated from these simulators to train your network to, predict the parameters from the data. And then, of course, at runtime, you give it another data set, and now you predict the parameters. And for me, not for me, but this is the same thing. So the whole point is that you want to condition on something and predict something else. So let's say, then, whether that's a parameter, and, again, for Bayesian statistics, it doesn't matter. Like, that's just a random value that you want to predict. I don't care whether, it's the value of a function or of a new data points, or it's a latent variable of your model, like, a parameter. It's just, it's a random variable that you want to predict. And so let's say, so the idea was to kind of put everything together so that The model doesn't care whether something is a data point, like literally a data point, or a parameter of your model, or anything. So you want to condition random variables to predict other random variables. That's kind of the mathematical idea. And that's pretty much it. And then, so we built it. And the idea then, say you need to train the usual way in which, you generate your data. You of course say the only thing you're doing is that, again, when we train our network, sometimes we give it only data and we ask it to predict the parameters that generate those data. Sometimes we ask it to predict other data. Sometimes we ask it to predict both. Sometimes we condition only on data. Sometimes we condition on data and parameters. So we kind of say, okay, these data were generated by these parameters. Now you predict these other ones, and so on and so forth. So since you do a mix and match of what you predict on, but again, you have this mix of random variables. But again, condition on something, predict something else. That's kind of the core idea. And then the other core idea is that a lot of tasks, and this kind of come, acts back to my origins in the sense that everything is prediction, everything is inference. So let's say a lot of tasks in machine learning are literally just conditioning on something and predicting something else. And now, not all the tasks, but let's say an overwhelming majority of tasks. So let's say, again, we have a few examples in the paper. Say image classification is prediction. Like, you want to predict like a label, which is, kind of like a big latent variable, kind of a coarse latent variable. In MNIST, you're predicting this latent variable, let's say, 0, 1, 2, 3, or whatever. And yeah, that's just, conditioning on the image and predicting. For example, in painting is conditioning on part of an image to predict other parts of the image. For example, optimization is I condition on the points I've seen so far, and I want to predict the location/value of the optimum, and so on and so forth. So so a lot of tasks is just you just need to kind of formalize in and figure out what you're conditioning on and what you want to predict, and that's your task. So let's say that's kind of the idea, which it goes beyond let's say the specific example we make in the paper, but say kind of it's broader, and and I still believe in it. So that's kind of paper number one. And the blog post, just I'll talk about it briefly. So the problem with this paper, I'll be honest, let's say it was a bit of on an issue, let's say, and we put too much stuff in the paper. Let's say that was actually, it's kind of like a capital sin in academia, because say people will read the title, maybe scan the abstract, but I say, of course, obviously, I mean, it's in a good way. That's that, yeah, nobody's going to check, whatever our appendix to see what else we did. And so that was honestly our mistake. So I say, so there are too many ideas in this paper, too many things. So I say, so for example, the blog post, I wanted to highlight some of the stuff which kind of went, a bit lost in the message. And which is, for example, our application. So as a side kind of minor thing we did, we had this whole section on Bayesian optimization. How overall, let's say, when you do optimization, let's say you can think of it as, yes, I want to condition on some data to predict the location/value of the optimum. And the point is, if you put it that way, a lot of existing methods that, for example, there are methods that so sometimes, for example, you have some hunch of where the optimum might be. So you might want to put that as a prior over the location of the optimum. Now, that's incredibly hard to do using Gaussian processes. So let's say, so you can define the shape of the EGP. You can tell, it's smooth, not smooth, etc. But telling a Gaussian process, okay, I really want the minimum to be somewhere here. Good luck doing that. So it's really hard. So there are methods that have been developed, for example, to do that specifically. Or for example, suppose that the optimum has value 0. For example, you're minimizing some kind of loss function which is defined mathematically, and that the optimum is at 0. So the value of the optimum is 0. So that should be giving you some information that you can exploit. Now again, putting that into a Gaussian process, very hard. In fact, there are specific papers that solved this specific problem, right? Okay, so how do I tell my GP that my optimum is at 0, or how do I modify my Bayesian optimization in such a way that the optimum I kind of sample from this region because I believe the optimum is around this region. So once you see it probabilistically, yeah, it's super easy. You have a prior on the location of the optimum. Yeah, okay, you can just put a prior on the location of the optimum, or I can condition on my knowledge that the value of the optimum is 0. Then, so in ACE, what you do, you condition on y star equals 0. You're conditioning on that, and you're predicting. And so anyway, so this we do as a kind of like a mini, like a side quest hidden in the appendix, pretty much. And so I say that should have been a separate paper, obviously. But I say, well, that's not how we were working at the time. So anyway, so that's why I wrote a blog post, because I want to kind of just so everything is about prediction. And so we can just, of course, it's the title is a bit of a provocation in the sense that it's not that easy. So there are some caveats, but let's say, it's an interesting way of thinking about it. Let's say, so essentially kind of think of your problem as a prediction problem, and how far can you go just thinking of, okay, I really want to predict this. Can I do it? That's it's not the full story, but say you can do a lot just with that.
Okay. Yeah. Yeah, and I encourage listener to check these blog posts out. It's really good. You can skim it and get the idea pretty fast. The links will be in the show notes for this ACE paper, this blog post, and also the ALINE paper. I do want to make sure you can talk about what you're doing currently. So maybe we'll be able to talk about ALINE afterwards. But first, you told me while preparing for the show that your group has several papers at ICLR this year, and you had a bunch of really practical things to talk about here, and you're doing very interesting things. So yeah, can you walk us through that and tell us what you've been up to lately and where your mind is at?
Okay, yeah, thanks. Yeah, so I'll try to be concise. So we have time here to touch about these different points. Yeah, maybe there are a couple of papers that are kind of more practical from our kind of iClear batch. One is it's called a PriorGuide, and the idea is, suppose that the result of pre-training that you can do, let's say in Amortized Inference, let's say you train your neural network model to do inference. So you spend doing this kind of relatively lengthy pre-training effectively, and then you deploy it, and then at runtime, okay, you give it a data set, and then you want it to, given this data set, for example, give you back the posterior distribution of the parameters that might have generated this data set. Now, it's a posterior distribution, and as the audience will know, obviously, let's say that depends on the prior and your data. So how do I specify the prior? So of course, let's say you can specify it at pre-training, but suppose that you're kind of pre-training your model, and you get some additional information later, which modifies your prior in the sense that or let's say another situation you can think of, especially kind of as we go towards foundation models for inference. Let's say someone else pre-trained the model, okay, with a specific prior, maybe a broad prior, which kind of accounts for many phenomena. But now, I want to use that model, let's say, for something more specific. So I know that, my prior is more specific. So if I use that broad prior, essentially, I'm kind of, throwing away information I could use. So how can I inject this information, when I use the model? Now, that's a big question. We try to do that also with ACE to a degree, but I'd say we kind of tackle more aggressively in this kind of more recent paper, PriorGuide. And the idea, essentially, we use the machinery of diffusion. I'm not entering the details, but say you had also an episode with Jonas Arruda, so it's probably very related. So the idea is that we use the machinery of diffusion to so you can use diffusion again as a method to give you a distribution. So let's say, we can do simulator-based inference to condition on some data, and then you do your kind of diffusion thing, and then let's say you get samples from your posterior. Good. Now, the nice thing about diffusion is that you can use guidance, which is kind of this technique, which essentially you kind of steer the diffusion, which the sampling in one direction or another, and if you kind of choose your guidance in some ad hoc way based on your problem, you can effectively have your model do different things at runtime. And the idea is that effectively just in a nutshell, that we found a way to encode the guidance which kind of moves the sampling in such a way that you can use a different prior at runtime. So you train, you or someone else trains the big model on a broad prior, like because imagine you got kind of foundation like, so it's very broad, many different parameters. Then at runtime, I have my experiment, and I know actually that the parameters tend to live in this region of space. I can put that prior at runtime using our technique, for example. And again, and it's part of a broader kind of area of research that we are really interested in, which is again this idea of test time compute. I mean, which of course is very relevant also to LLMs, but say, so essentially, how can we add information or additional computation at runtime? Before I was saying, we want to amortize everything. That was a few years ago. Now I kind of, there is a caveat to that. Let's say there is an addendum. Let's say that so maybe we cannot amortize everything because that would mean essentially kind of pre-compress the entire universe in a single model. And maybe we cannot do that. There will always be some situation that you have not quite encountered before, and you need to kind of spend computation at runtime to figure out what's going on. And so essentially, so we're kind of following the trade, in a way the steps of LLMs and agents, in the sense that so you do some pre-training, but then you probably also want to spend some time at runtime because you have some information that you get only at runtime, and now you want to use it. So PriorGuide is just one specific instance of that. There might be, there are surely many others that we are exploring. That's what kind of, so it's part of a broader agenda. So how do we do, amortized inference? But again, not everything is amortized. Something might be changed at runtime, etc. So it's very exciting because there's a lot of stuff that can be done. And the other paper that I want to mention very briefly is this efficient autoregressive, inference for transformer probabilistic models. And actually, kind of the tagline is very short. And the idea is that, okay, so I discussed before how it's important that all these models kind of preserve this set property. So let's say, so you can kind of move around your data points, and but let's say your prediction doesn't depend on the ordering of your data because it's a set. Now it turns out that that's all very good and nice, but it makes really nasty, effectively kind of expanding this set. So if you have got more data, since it's a set and it chooses kind of this self-attention, which is kind of between all the points, every point that you add, you need to recompute everything from scratch. So there is no concept of, for example, KV caching, which is kind of a staple of modern transformers and modern LLMs. The idea that okay, you kind of store some computation you've done so far, and you only need to compute the additional tokens that you learn. So the idea is that, of course, we could do that, but we would possibly possibly lose something. So the idea is that, okay, so what if we use this idea of a buffer, in the sense that so we keep the context, fully, set based, fully self-attention. Then, we can add kind of something which doesn't do full attention with the entire set, which would require us to recompute everything, but effectively only does what's called causal attention, which means that each tokens kind of only watches the previous tokens. So now this is not permutation invariant anymore. So we are kind of breaking this permutation invariance. But we are doing it only for kind of these additional points that you add. So the idea is that you kind of add new points very quickly, and you can make predictions very quickly for new points. And then, once you're done with that, you can kind of, okay, now you have time, you can put them back into your set. And now you can use low update, in which you update everything. So kind of, and this actually has a lot of usages because it's kind of, so you can keep your context, permutation invariant. Then you can do a lot of kind of, even in parallel, you can literally sample thousands of points using this technique, and then let's say you can kind of merge it back, all the information back into your context. Anyways, so it's maybe in a way it's kind of more a kind of architecture, more engineering in a way. Let's say there was a lot of problems that need to be solved, like engineering wise, but it's something that we're kind of building on, because it kind of lets us, again, it's an unlock because we can do a lot of things with this now.
Damn, yeah. Yeah, we definitely need the links to these papers in the show notes. So what are the cool things we can do now with that? Like, what are you working on right now based on these papers? I'm guessing you're trying to add some of these possibilities to some packages. So yeah, what are you planning around that to help people use it?
Well, so the grand vision here is that we've been discussing, say, my group. Let's say, I have the, I can show the logs. I've been talking about foundation model for inference for many years, and so that's something we've been kind of discussing for a long time, and that's always been kind of the the North Star for us, for my group, essentially building exactly this foundation model for inference. And in order to get there, we kind of need to solve a lot of problems. Shout out, of course, goes to what have become foundation models for inference recently. Recently, past few years, all the tabular foundation models have been have shown us the way how you can build a foundation model for inference. Of course, they apply to tabular data, but a lot of things can be put in a table. So let's say, from my perspective, let's say they're general purpose foundation models for inference. Let's say, even though people cannot call them tabular data for historical reasons, I guess. But let's say, so you can apply them to a lot of things, and and they've been doing amazing. So we are very interested essentially in that direction, to expand in that direction. And there are lots of things that you can do. Let's say, but so of course, let's say there is a lot of new ideas that can be tried in the space. And luckily, these models are still fairly small, let's say, compared to LLMs. Let's say, so they're still nicely within the reach of what we can do, again, within academia. So we don't need to spend, millions or hundreds of millions or billions to get training done. So let's say, so that's quite exciting, because let's say, so we can still contribute. And for example, just to mention, the buffer that I just mentioned, can be applied to transformer, neural process, etc., but also to tabular foundation models. So let's say, one particular thing that you can do with this fast prediction that doesn't require you to recompute everything is unrolls, which are very useful for if you're doing reinforcement learning. So say, so if you want to do fast predictions to see what happens as you add more data points, and you want to do RL on this, what we built allows us to make it like 100 times faster or something like that. So with much with 100 times fewer memories, like it's super useful. So let's say, so that's something we're going to use, definitely. Also others can use. And just mention a direction. So a lot of the things we are doing are part of a grand plan, and we're building one step at a time. But let's say there is an arc where we're going towards.
Yeah, actually, you want to talk about that long arc, or do you want to talk a bit more about ALINE, whatever you want, because I do want to be mindful of your time and start playing us out here.
Yeah, thanks. So I'll give you maybe I think ALINE doesn't take a lot of time, and actually it's a good segue to discuss more on the foundation model direction. So the idea of ALINE it was to take what we did with A's. So let's say you can predict things, you can condition on things, you can predict things. And now we add the fact, okay, we also want a model that does active data acquisition, which means, because ACE is passive, it's just doing Bayesian inference. You just feed it the data, whatever data you have, you feed it whatever information you have, and then, it does predictions. Now we also want to collect data, do active learning or experimental design, which means essentially you need to select which points in the space. And again, Bayesian optimization is a form of active learning, right? You're sampling points in the space so that you want to find the minimum. So that's what we want to do. We had some work before with Dowlang, and this is done, of course, work done with particular with Sami Kaski at University of Aalto University, and so Dowlang is a PhD student shared between Sami and me. And the idea is, okay, so let's use effective reinforcement learning to train another head on top of, let's say, an ACE-like model that instead of predicting just the value, say data predictions, it works as a policy head and tells us which points to collect. And what's the goal here? Well, the goal here, for example, can be our ability to predict other data points, and this is kind of self-reinforcing in the sense that you have one head that makes predictions, then the other head that computes the policy that lets you predict better. So let's say, so these two loss functions in a way work hand in hand, and so we have a single network that does both. And of course, it's both convenient in the sense that, okay, so now you have a single network that, essentially you can use it for data collection, and then you can also make prediction with it. Nice. But I think it goes deeper than that, because now we have a single network which is learning to do these tasks, and these tasks help each other in the sense that the prediction head is actually used as a target for the policy head, in the sense that, use the policy head to want to improve the prediction, to make, for example, more precise, improve the they prove the log density, etc. So that's just, again, it fits. There's this nice synergy between the heads. That's the idea. Then, this trained via, reinforcement learning, so on and so forth. So then, there are also kind of technical aspects, but it's, kind of the high level idea is this one. And then, but this brings me to the kind of foundation model idea, because if you look at many, say, the modern foundation models, like, again, I think this, and again, in this field, you can think of tabular foundation models, because those are kind of, what occupy the space. Of course, there are others. The point is, they do prediction. So you just, fill in more points, etc. But as I saw, the vision I have for a foundation model is more than that. It's so of course, there's a core of prediction and inference. Of course, as we said, it's very important. It's as the base, the basis, well, the base of everything. And sorry, I had to do that. But the point is, we want to do tasks with it, right? So say you want to be able to do, for example, again, Bayesian optimization is an example. Experimental design is an example. Again, the goal is not similar, so it's not the same, but it's similar. So you want to collect data so that you want to improve your predictions for for certain parts of your space, for the parameters. So you have a task. So and the point to me, let's say that's these goals are not kind of an appendix to the model, but I say I see that as part of your foundation model. So your foundation model, say has an array of tasks that is trained to do. And the point is, I mean, again, and this is where I think, let's say, we will benefit from the magic of meta learning, in the sense that the model, again, if it's big enough, it's learning all these kind of representations to do all of these tasks, and the point is kind of using them, right? So it's learning to generalize between different, or at least interpolate between different tasks. And then, of course, I kind of spilled the beans in the sense that, so of course you hope that, then at some point you start seeing some degree of generalization. And, so essentially as you do more and more tasks, not just prediction, but other tasks, let's say, you get something more. And again, we have glimpses of that with, with agents, LLMs. Let's say clearly, of course, yes, they, again, it's very jaggedy, as we know, etc. But still, let's say, I mean, they're definitely not just literally doing what they're training on, but there's a bit of, jagged generalization, and maybe limited, but still, I mean, I'm pretty sure, especially a lot of the problems that I use them for, they've not been trained exactly on that. So anyway, so let's say, again, can we do something similar? What that even, what would that even look like? Like, so it's not obvious, right? So let's say there are many open questions here, and I think, let's say, but that's what I see as the big direction. So eventually, again, the dream is this kind of big Oracle foundation model, which, you can, and LLMs might be a part of it. I know that you asked, discussed it with this Stefan, and I think maybe we have a slightly different version of that. Of course, I say yes. I totally agree with, agents that, like modern agents that just use kind of Bayesian tools as, let's say, as tools, and that's definitely, let's say, I see that totally happening. But also say I think we can also push on the concept of big models for inference that just are focused on doing inference and learning to do inference, and and they're good at doing inference. And then maybe these models can be then called by agents. Okay? So the two things are not kind of opposed.
Yeah, exactly. I think we spoke about that at length with Stefan during 2 episodes. So definitely recommend listeners listen to these ones. The one with Jonas Arruda also was a bit more focused on diffusion models, and he also did a live demo. So definitely recommend that one too. And in general, really agree with what you just said here, and I think it's a very important and interesting part of your research, not only yours, but like your whole group, where that's really interesting to see how the LLMs and agent part are merging with the amortized inference part and the more Bayesian models side of things. And actually, of course, you've been working a bit about that right now. You're also doing some work on LLMs and agents. So what I'm curious what you're mainly doing right now about that, and what was the question, that pulled you in, and how do you see it connecting back to amortization and probabilistic conditioning?
Yeah, so the work strictly on LLMs and agents, let's say, is still in stealth, I would say, in the sense that we haven't
Okay,
published. So let's say,
interesting.
so we are, yeah, we're working, and let's say that's ongoing. And although let's say, so it's an idea that, some of these ideas have been kind of going back and forth. But let's say, so the angle that we were exploring at the moment is related to, there was recently a position paper. This idea, say, the idea I've been working on, let's say, we've been working on, let's say, come earlier, but of course, let's say, it's in the zeitgeist. And so let's say, so there was this kind of large position paper recently that says, we should think of agents as, say, in the context of Bayesian decision theory. And more than ever, effectively, we need Bayesian decision theory because essentially that's what's happening. Is they're making kind of small decisions all the time, constantly. And so let's say, so that's kind of was the hook for me, was kind of start to play around with local LLMs, small agents, because let's say I'm interested in resource constraints. We haven't talked about that at all, but it's one line of research in computational neuroscience has to do with essential inference under resource constraints, and we have some work on that more on the neuroscience camp. But anyways, but let's say, so I think that's very interesting because say there is this idea that intelligence kind of arises under boundedness of resources. So let's say, so you need to the idea that the fact that we need to compress memories actually makes us kind of generalize, because say we need to kind of compress things to then generalize. Anyways, so I think the whole idea of constrained resource constrained system is very interesting in itself for a whole lot of reasons. And so let's say, so for these reasons, the local LLMs or small LLMs or tiny LLMs even are very interesting, because you want them to be able to do things, but of course they're very limited. So let's say, so how do you make them more usable, more reliable? And well, it turns out that I have a lot of work on sample efficiency, etc. So essentially, so I've been kind of combining these ideas from sample efficiency in the kind of small, LLM world, but I say, of course, the application mostly would be for small LLMs. Also because they're local, you can play around with a lot of stuff with the way in which you sample tokens from these. And to be concrete, for example, if you think about what small LLMs do or small agents do, for example, when a small LLM, in general, also agents in general, decide to call a tool, effectively, it kind of needs to emit a token. Okay, I'm calling a tool, and there's a specific token for that changes depending on the family. And and then it says, so okay, now I'm calling a tool, or I'm not calling a tool. And if I'm calling a tool, okay, then effectively, for example, tool name, it's another kind of token, or maybe a few tokens. And you can think of that, as kind of small choices or small decisions that are made, and they are probabilistic, in the sense that, well, first of all, they're stochastic, because LLMs tends to be stochastic, unless you put the temperature to zero. But also they're probabilistic in the sense that they're based on limited information. So you can think of effectively you can build a posterior over this, and and work with that and do kind of the old Bayesian stuff. And so anyway, so it's that's kind of the things that we've been exploring.
Okay, very, very interesting, very cool. Definitely sounds like worthy of another episode when you guys have that out. Yeah, so as listeners probably know, I've been also working myself on some Asian stuff. I'll refer you to at least episode 157 and 158 with Stefan, but also you can check out the blog post section of the website, because I've also worked on a Bayesian workflow skill and a causal inference skill. The one with Stefan was really about the amortized workflow skill. And yeah, that's also why I love talking about you guys do on the show, because it's also something I work on myself, and I think has a lot of potential to help people in the future and make sure the good practices that come from latest research actually gets distilled into the general public. So yeah, thanks a lot for doing that, Luigi. And actually, I'm also curious, to finish on a practical note for an LBS listener who currently lives in Stan or PyMC or NumPyro. Where should they actually start with The tools we've mentioned today, so mainly PyVBMC, PyPads, BayesFlow, what's the smallest interesting problem to try first, you would say?
Yeah, that's interesting. So yeah, these essentially the tools we discussed, and then BayesFlow essentially, which which kind of like a general purpose amortized inference tool, kind of apply it to mildly different situations, and we've been trying to kind of combine them in the sense that with our amortized Bayesian workflow paper again with Stefan and others, and it was led one year by my now graduated student Chen-Kun Lee, and so ideally you want to start actually with amortized methods because they're, especially if you have many data sets to analyze, that you can have a very strong win there, because if you have many data sets to analyze for the same model, then you would need to run MCMC or any method from scratch, and that can be very expensive. So let's say amortization would pay off. So let's say if you're in that case, let's say you should consider using amortization. And then for example, I mean, of course it's a bit of a plugin, but we have these ideas for how essentially you can then check whether your amortized methods say your amortization has worked, and or you can trust it. And the point is, of course, if you don't trust it, then for those specific data set that you don't trust, those posteriors that you don't trust, then you can do kind of MCMC, and in a way which, by the way, is supported by amortization, so you can use amortization in some way. So that's essentially kind of a natural way for example, someone who does MCMC and does not trust amortized methods. And fair enough, let's say I understand where this kind of mistrust can come from, in the sense that, of course, MCMC has built a lot of diagnostics over the years, and it took many years to come to the modern diagnostics, right? So let's say that's that's something we in the community are building also for amortized inference, right? So because again, understandably, in order to use a method, you need to know when the method failed. It's probably one of the most important things to know with a method as a practitioner. And essentially, many data sets, then you should definitely consider amortization, because that might really kind of speed up your workflow. And let's say if you look at our tricks, our suggestions, then you can still kind of trust the whole process, because in worst case scenario you kind of go back to MCMC for those specific problematic data sets. That's one thing. Then there is the other angle, which is if your model is, as we discussed, let's say expensive in the sense that each evaluation of your log density of your model takes time, or has a cost of in some sense. Typically the cost is time and computation. Then then you're in the case in which you might want to look at, for example, PyVBMC. And to be honest, I'd love to connect PyVBMC more to the PyMC and BayesFlow environments, so that they could kind of speak more to each other. And that's something that we've been discussing, but we haven't managed to do yet. But now with the agents, maybe we can kind of speed that up. And so since we have something expensive, etc., then definitely, let's say you might want to consider methods that kind of do efficient Bayesian inference, in the sense that they can get you to an answer with a relatively small number of evaluations of the log density, like again of the order of maybe up to a few hundreds, and that can be of course kind of very useful. And finally, I would say but of course that's not something necessarily I would say for in a Bayesian statistic podcast, where so there are people who don't care about say for that number of reasons, let's say they might be okay with a point estimate. And of course there are reasons to find a point estimate, because for example even if you're doing if you want the full posterior, doing like a rough optimization, maybe you don't want to start exactly from the map for a number of reasons, especially if you're in moderately high dimension. But if you're in a relatively low dimension, there's nothing particularly bad in starting near the map, like the maximum a posteriori or mode of your posterior. And in typical actually it's a decent starting point. Again, in low dimension. In high dimension things are very different, so you shouldn't do it. But let's say in low dimension, let's say, so again how do you start from the mode? I mean, you can run optimization. And in fact, let's say that's, for example, how many practitioners use kind of PyBuds in combination with PyVBMC. So first, they run optimization such that they would kind of find, a place near the optimum, which would be the mode, and then start PyVBMC from the mode. And that works well because, as we discussed before, typically the posterior is kind of nice near the mode and might be quite nasty elsewhere. So if you were to start PyVBMC or even MCMC from farther away in the tails of your posterior, things can be quite nasty and bad, and you'll say have kind of all sorts of numerical issues. But if you kind of start near the mode, things are nice. So anyway, say that's how kind of you can kind of this nice synergy again within PyBuds and PyVBMC.
Yes, definitely. And I know also some work has been done lately, especially by Alex Fengler, who will be soon on the show. I'm working on that, making a bridge between PyMC and BayesFlow. And so, yeah, definitely that resonates with what you've just mentioned. Fantastic, Luigi. Any other topics you would like to discuss?
One thing I say, but I want to kind of state again is that the motivation here is always practical in the sense that we want our tools to be used, right? So we are not doing. I mean, as much as the theoretical aspect is very interesting, but let's say so we want to build tools. So say, yeah, so if you kind of need to categorize what we do in our lab, we definitely we are tool builders, and we build even complicated tools. But the idea is that eventually we want people to use what we're doing. In the case of, for example, some of our methods, say it's kind of taking a bit longer because say we are kind of building towards the releases in a way of things that we can actually recommend. But yeah, we will I'm very confident we will get there. But say so the feedback from users, etc., it's actually super important for us. Like what are the interesting problems, and also if a method fails, let's say we are actually very happy to hear, and I've been in touch with many users, like to know what works and what doesn't, and and it's kind of keeps research very healthy because say okay, these are the problems that people care about.
Yeah, I definitely resonate with that. As everybody knows, that's also why this show is here. So thank you so much, Luigi. That was really great. And same, I could do a 6-hour episode with you, but I feel that would be much better to do it in person. So let's postpone that until
I look forward to that.
I visit Helsinki. Yeah. In the meantime, I'm gonna ask you the last two questions I ask every guest at the end of the show. So first one, if you had unlimited time and resources, which problem? Problem with my mic. I'm telling you today he's a bit. Okay, so let's do that again. In the meantime, I'm going to ask you the last two questions I ask every guest at the end of the show. First one, if you had unlimited time and resources, which problem would you try to solve?
Yeah, I had to. Well, I mean, okay, so I can give you the kind of gut answer, which is if you look at the title of the name of my group is called the machine and human intelligence, and it's not just a fancy name in the sense that the underlying kind of the fil rouge, the connection, is that I'm interested overall in how intelligence works and not necessarily the human intelligence. That's the point, right? It's machine and human, or say so, and even an animal. So let's say so for me it's kind of all the same in the sense that it's some sort of general concept underlying say how do intelligent agents work, how does that arise? And of course, let's say the work I've been doing, let's say, is kind of takes a specific angle, which is intelligence has to do with inference. It's which of course, say it's kind of it's a very opinionated take on what intelligence is, and of course, say it doesn't end there. But let's say there is you can say it covers a lot, and some people say it's actually everything there is. There are active inference, camp, etc. But anyways, that's all another discussion. And so big question is, okay, what's intelligence? How does intelligence arise? So what makes a brain work intelligently, and like an agent, and then people are asking, are modern, say, as of 2026 agents intelligent. Some people will, scream and say, no, that's not intelligence. That's, whatever. That's, just token predictions, which, and other people will say, yeah, of course, I see some elements of intelligence, etc. So anyways, so understanding what's the secret of intelligence, I think that's one of the most interesting questions.
Yeah, definitely agree. That would solve a lot of problems also, as a trickle down effect. So definitely agree. This is a good one because it's not a contained solution. So very interesting. And second question: if you could have dinner with any great scientific mind, dead, alive, or fictional, who would it be?
Yeah, that's a hard one, of course. And so again, I didn't give it too much thought because otherwise it's kind of cheating. And I would say Johnny von Neumann, and as mostly because essentially I'd be interested kind of pickle his brain, which is of course famously very, very big and a smart person, and what he thinks about the modern developments in artificial intelligence, etc. I think he'd be very fascinated by it. So I don't claim I would be able to kind of match in any way his intellect, but I would definitely kind of benefit from given the insight that we have just by being born in this area and having seen this explosion of artificial intelligence. So what does what would he make of it? And I would be very interested in that.
Yeah, for sure, and for sure a dinner where there is a lot of things I would not understand. So let me know, and I'll come.
Yes.
I will for sure learn a lot. Awesome. So please make sure to add the latest papers you've mentioned in the show notes, because I have the ones from last year, but not the ones you've been working on this year. So add that to the show notes. I'm sure people will look into that. So yes, listeners, make sure to look at the show notes if you want to dig deeper. And Luigi, thank you again for taking the time and being on this show.
Thank you. It's been a pleasure.
This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and follow the show on your favorite podcatcher, and visit learnbaystats.com for more resources about today's topics, as well as access to more episodes to help you reach true Bayesian state of mind. That's learnbaystats.com. Our theme music is Good Bayesian by Baba Brinkman, feat. MC Lars and Megaran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. You can support the show and unlock exclusive benefits by visiting patreon.com/learnbaystats. Thank you so much for listening and for your support. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.